Next up, we have Professor Tina Eliassi-Rad. She's Associate Professor of Computer Science from Northeastern University. She's also a core faculty member at the Northeastern's Network Science Institute. She's published very widely, over 70 peer-reviewed articles in this area, and some of her algorithms have been used in the industry. And we're very delighted that she's going to talk about just machine learning.
Great. So thank you, Matthew, for inviting me to speak to you about a project I have called Just Machine Learning. If the title seems ambiguous to you, it's by design. So as was mentioned, machine learning, the phrase and the field go way back to 1959, where Arthur Samuel defined the field the way Matthew described it earlier, which is field of study that gives computers the ability to learn without being explicitly programmed. And the very first machine learning program was the Samuel's checker playing program, where it wasn't doing machine learning the way we think of it now. What it did was it would memorize every state that the game was in with a terminal reward of having been in that state. And of course, machine learning from the academic perspective is this nice interdisciplinary field, which it touches many other disciplines. And if I have forgotten your discipline, it's just because I didn't want the flower to be too crowded. But in practice, as Matthew mentioned earlier, you have this cartoon. And the one thing that I just want to point out here is that the answers looking right or wrong have only to do with accuracy. It has nothing to do with the moral status of the answers, whether the answers follow some ethical guidelines or whether the answers match some cultural norms that we have. So the way I like to define machine learning and think about it is by thinking about the well-posed learning problem. And perhaps it's because when I first started learning machine learning in depth back in the 1990s, I was one of the guinea pigs that read preprints of this textbook by Tom Mitchell. So Tom Mitchell defined the well-posed learning problem as a triple. You have a task, you have experience, and you have performance measures. And the idea is that the computer program is said to learn on the task, given the experience, if its performance, as measured by the performance measure, gets better over time. So let's think about the task, the experience, and the performance measure. So those are going to be our three pillars as I go through this talk. The task. So one of the things to pay attention to is the algorithm learning for the task that you have defined? There have been very well-known cases way back from the 90s to recently where, for example, the Department of Defense in America wanted to distinguish between tanks that were camouflaged and tanks that weren't. And it seemed that what the algorithm really learned was whether it was cloudy or whether it was sunny. Or recently, the bad science that came out of Stanford about, oh, we have a deep network that looking at images can tell whether somebody is gay or not. It seems like what they learned was that gay people tend to have photos that have better lighting, right? So one is just auditing whether the machine learning algorithm learned the task that you wanted it to learn, and that itself is not an easy endeavor. Now, thinking about this field of algorithmic bias and fairness in machine learning. And I know that nowadays when people say artificial intelligence, they really mean machine learning. And so I'm going to be careful in terms of my use because I studied AI when people cared about planning and knowledge representation and automated deduction and so on and so forth, right? So we're talking about machine learning. So what are the two popular tasks that people have been looking at? One has been assessing risk, simple classification, right? What is the risk of Tina committing a crime? It's 8. It's usually from like 1 to 10 kind of a thing, and then some kind of a threshold. And the other one has been ranking. So I want to, and this is inspired by, for example, web search. I want to produce a rank a list of pages that are less biased. You probably have know of Latanya Sweeney's work, where when she went to Google and types in her name, which is African American, then the ads come up as bail bonds, so on and so forth. And so there's been this movement in terms of ranking. Now you may say, why these two particular tasks? One is because machine learning people know a lot about them. It's low-hanging fruit, right? We live in a world right now where people only go for low-hanging fruit, it seems, as opposed to solving the hard problems. This is partially by the incentives of the funding agencies. So that's one. And the other one is that the human decision maker seems to like these kinds of risk assessment numbers, right? For the judge saying, hey, Tina's 8, Bill is 2, blah, 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 they can go through the cases as quickly as possible, right? And in fact, in a lot of the algorithms that are out there, they do not give any kind of uncertainty scores. And there have been cases where the judge overturns a plea deal because the algorithm said 8. And this idea that the algorithm is objective, and what if the judge lets the person go and then the person commits a crime and the judge now is on the front cover of New York Times because it didn't listen to the algorithm. However, perhaps if the judge or the human decision maker gets a risk assessment with some probability that maybe Tina's algorithm is only about 65% sure, then they would have some wiggle room in terms of the decisions that they make. So there have been a lot of issues, especially in terms of assessing risk, which is a big task that people like. For example, I was at the NIH Bioethics program. It seems like most of their tasks are assessing risk. So in particular, there was work that Cheldakova, who is a professor at Carnegie Mellon, had, which it said that you cannot have a model that satisfies the properties that I'm listing. So if you have unequal base rates, so for example, women get breast cancer more than men, and you have mutually exclusive groups, so you divide the population by males and non-males, and you have an imperfect classifier. In fact, for her, she didn't need imperfect classifier. It was just statistical parity. And then 3 measures of fairness that people really like: precision parity, true positive parity, and false positive parity. You can't have a model that satisfies all of the X's. And then Kleinberg et al. Around the same time extended this where they took away statistical parity and they said, what if I have imperfect classifiers and non-identical variables? And recently with Brandon Feidelson, we were able to take away one of the requirements that Kleinberg et al. Had, which was mutual exclusivity, like males and non-males. So you don't even need that. So you could have a population where, for example, somebody like Obama is both white and black. And so he belongs to multiple groups. So there are issues in terms of the defining the task as risk assessment and then trying to satisfy certain fairness measures. So what has been the fallout? The fallout is computer scientists are very good at bastardizing things because we need them to work, right? So what people have done is, well, what if I get rid of one of the parities, right? Or what if I have some bounds in terms of how bad some fairness measures are? And recently at a meeting, Deborah Hellman was talking about, well, if you are going to get rid of one of them, which one should you get rid of? And trying to connect these fairness measures to what you ought to believe and what you ought to do. And she's writing a book about this, and her takeaway message was that if you're going to drop a parity, drop precision parity, because that gets at what's called the right-making properties. So usually being a white male is a right-making property, it seems, in our society, and so that's what you want to get rid of. So the first set of problems have been these ideas of, well, if I do risk assessment as a task, then I can't have certain fairness measures that I would like to be satisfied. The other problems is that the tasks seem to be too abstract in terms of too under-described to have any kind of real moral or ethical consideration. Basically, you're either sorting or ranking. So if you think about classification, it's really sorting, right? Tina goes into this bucket, Brandon goes into that bucket, Ben goes into that bucket, so on and so forth. And so far, they don't provide any uncertainty values to the human decision maker, and it could be because people are notoriously bad at reasoning about probabilities, and so they want to make it or keep it simple. And the last thing is that they usually don't provide any kind of context for the human decision maker. For example, the famous COMPASS data that a lot of people have worked on, it's just a data dump over 30 years, right? It doesn't take into account that policies were changed or laws were changed or maybe cultural norms were changed. And so you're trying to sort people based on 30 years of data where during that time laws and policies changed. So one approach that my lab and I have been thinking about has been in terms of learning to place to address these three issues. So, and this is with a graduate student at Network Science Institute, Shindy Wang, and a postdoc, Honor Baral. And the idea is that society usually defines a spectrum for us in terms of better to worse, and it places us on that spectrum. And so what we would like to then do is when a new instance comes about, we want to figure out where that new instance should place. And of course, we are not assuming that instances lie on the spectrum in a Gaussian way, right? You're going to have heavy-tailedness where you're going to have more petty theft and less first-degree murder. But the idea is that you are able to place people on a spectrum, and as a new case comes in, you want to know where to put this new case. It was very important to us to have an interpretable model. Recently, Andrew Gilman at Columbia had a blog post about explainability versus interpretability, and he distinguished them in terms of explainability being, I'm trying to make sense of the output given the input. Interpretability is, I actually want to see what the model is telling me. And so we have this two-phase approach. The first phase is is one case better than the other case, right? So you go to human beings and you say, is Tina better than Brandon, right? Just this yes or no business. And so then you're able to learn a classifier that can learn preferences. And the second phase is then placing this new item in your spectrum. And so here's where you can have some conflicts where the classifier, because it can make errors, it's not a perfect classifier. It could say that the new item is worse than item A, or it can say that the new item is better than item B. And so you need to be able to resolve conflicts. And so what we do is we have an approach that's similar to maximum likelihood, where we actually see where the votes lie in terms of the intervals that we have on this spectrum. And we say that, well, the new item falls in the interval that has gotten the most votes from the classifier. And so then to the human decision maker, we can say, well, look, at the new item falls between item 1 and item 3, and this is my confidence about it falling in those items. This also slows down the human decision maker, because then the human decision maker has to go and read item 1 and item 3, and that way try to see if he or she wants to make a decision about this new item. As opposed to, again, item 4, which is the new item, has a risk estimate of 8 without anything else. And so partially what we've been using this learning to place approach has been to audit fairness. And so we have these experiments we call normal experiments and cross experiments, where if I have a population, in my normal experiments, my train and test sets come from, for example, the red people, right, or the blue people. So there is no difference in terms of these protected characteristics or sensitive features between my train and test set. And then we have these cross experiments where the model is trained on one set of training data, for example, on the red people, and then is tested on the blue people. And what we want to know is we want to know how the errors of models are different and how varied the errors of models are. And so for us, the performance measure is not classification, it's actually regression. I think classification has other problems in terms of where you put the threshold versus regression of, for example, how many days until Tina commits another crime is a straight up regression problem. And so obviously, there is a predicted value that the model gives, for example, the model that was trained on the red people, and then there's an actual value, right? And so that would be the error for the model that was trained on the red population. And so then you have this over-prediction and under-prediction. And so here then, in terms of what is considered fair, is that it should not matter whether the model was trained on the green people or on the blue people, right? When I send Tina to the blue model, I will like to get the same kinds of errors as when I send Tina to the green model. And so what we want to do is measure deviations from this particular fair line, right? And so this is on the COMPASS data, and just to show you, for example, where people fall when you are doing, so this is testing, over there is testing on white people, and error normal is when you train on white people and you test on white people, and error cross is when you train on black people and you test on white people. The thing which is interesting here is you can actually measure if the errors you're getting are coming from different distributions. And so this is what we see here in the second row, is that the errors that the model is making are actually coming from different distributions. Both the entire error, also the over-prediction and the under-prediction. And one of the things that this tells us is that then we can, for example, try to quantify favoritism and prejudice depending on the task. And so we can compute the differences between the errors on the cross model and what we're calling the normal model, find its density, and then say, okay, well, if the error is on the positive side, depending on the task, I'm going to call it favoritism. On the negative side, it's prejudice. And one of the things that then you could do, this is again on the COMPASS data, is you can measure the amount of variance and difference in terms of the favoritism and prejudice that you're seeing. And I'm not going to show more results to you. You can go to that URL and see a lot more results. But what is interesting is that we can track this variance that we see and see where this variance goes. So on the COMPASS data, for example, we saw that the variance that we're getting in terms of errors of the models tend to go to black females, then they tend to go to black felonies, and then they tend to go to people between 21 and 25. And why would you care? Because then if I have somebody who's conducting an audit, I'm going to say, go and look at the cases for black females. Because there seems to be that the model is making the most error. The spread of error is very large. Why is that? We don't see as much of a spread among whites in any population. It seems like whatever decisions are made about them seems to kind of be straightforward in terms of what the model is able to learn. So this seems okay. I am in the business of coming up with algorithms. Here's one, seems simple and maybe useful, but it still has some issues. In particular, what I really would like to do when people talk about fairness in machine learning or ethics in machine learning is to learn the processes of human decision making. What I would like to do is be able to have a machine learning algorithm that learns what a human exemplar would do, as opposed to just a dump of data over 30 years with no context. Now, if I want to learn what a human decision maker will do, then I need to figure out what are the incentives and the values of the human decision maker, right? Is it profits? Is it efficiency? Is it accuracy, right? Is it reliability? Is it that I make fairer decisions? Is it all of them? Is it none of them, right? So that is one that needs to be looked at. And so the other thing is that it seems to me that in many of the cases that machine learning is now being used for human decision making, there's this notion of apprenticeship, right? My older brother is an ophthalmologist, and when he was in medical school, we were living together, and it seems like in America, the medical profession at least, is very much this apprenticeship, right? You have the attending, then the fellow, then the residents, and it's like ducks, right, going all the way down, and they learn from each other. It's the same thing, it seems to me, in law as well, where you clerk for somebody, right? And so this notion that perhaps what I really want to do is I want to imitate how the human being makes a decision, And at least that would be one framework to look at. Now, in machine learning, we do have a task called apprenticeship learning or imitation learning. But that task is a hard task. It is not as simple as risk prediction. We're really good at that. But not in terms of imitation learning because it's a much more complex task. And so what is apprenticeship learning or imitation learning? Basically what you're trying to do is you're trying to learn from demonstrations. Or, for example, you have somebody that is following a doctor and seeing what kind of decisions that it's making, and maybe is able to also ask why the doctor made certain decisions. And so then the goal would be to learn a policy that would mimic the demonstrations. There's a really nice tutorial that was in the International Conference of Machine Learning that you can go if you're interested in learning about imitation learning or apprenticeship learning. But the ingredients are basically the input or the experience, which are these demonstrations, the environment or the simulator that is saying this is how a hospital, for example, works, or this is how an operating room works. You have some policy or hypothesis class. So, for example, you're saying that I want to learn the policy on the hypothesis space of decision trees or of polynomials of degree 10, which is not a good thing to do, but or of a deep network, right? But that kind of a thing. And then you define a loss function. This is an objective function, right? So machine learning people live and die by the objective functions, right? What is your objective function? And then you have a learning algorithm. You probably have heard about backpropagation that tries to learn on that hypothesis class, right? Seems simple, but it is actually a very hard task. And so there have been people who have been talking about this. So Mike Littman, who is at Brown now, who's one of the key scholars in reinforcement learning, had a nice paper a couple of years ago. Then there was value alignment that was mentioned as well. And also some folks at Technical University of Munich from robotics have also this idea of virtue ethics, right? Can I build in virtue ethics in my robots? Again, if you look at these papers in terms of their experiments are on toy problems, right? They are not on real problems that, for example, you would have in a hospital. But it's an area of growth. And the point that I would like to convey is that we should think about what the task should be, as opposed to just say classification or ranking, right? And in fact, this is where talking to people who are not machine learning people is great, because you come from a different perspective than the straight up classification, regression, and so on and so forth. So the next thing is experience. And so there's been a lot of work in terms of this. Joy Bugliamani, who is a graduate student at MIT Media Lab, if you haven't checked her out, you should. She's awesome. She coined this phrase, the undersampled majority, where the majority of people in the population are not white people, especially white males, but the training sets are often white males, right? And one of the things which is interesting here is that in many of the works that are out there, when you measure error in terms of the error that the machine has made, the cost of that error is not uniform, right? So when Google made the mistake of labeling an African-American lady a gorilla, that costed them a lot, right? And in healthcare, there's also this idea of different costs. And so there's lots of them. And so here, if we are to learn from demonstrations, how should we represent the implicit and explicit biases in human demonstrators, right? And there's a nice paper by Gabby Johnson, who is coming to NYU on a Bursoff Fellowship next year about the structure of bias, which as a machine learning person, the way I read it was that implicit biases are basically training instances that are in my head, and from time to time I make inferences from them. And the explicit biases are the rules that are in my head. And so a lot of the inconsistencies that perhaps you get from human decision makers are because of these inferences that I make from my implicit biases as opposed to explicit biases. And then, should we learn from simulations, right? Can I actually do modeling and simulations? In computer science, we know a lot about modeling and simulations of how a real scenario is and learn from what I would like the world to look like, right? So to try to get my training instances and my demonstrations from what I like the world to look like and not what the world is currently. And the other thing, which is of interest to me because I'm part of network science, I like to think about data that has nodes and links and relational dependencies, is how does your friendship network affect what happens to you, right? We all know that when you go to a doctor and you start chit-chatting, and if you make a human connection, perhaps because you went to the same university, right, it seems like the doctor cares about you more then. Right? And so how does the networks come about? And so we've done some work in terms of criminal justice, in terms of how far does prejudice spread in a network. We all know, for example, in academia, if you get your PhD from a top lab, that positions you well, right? It is not that you are inherently better than somebody whose PhD is not from a top lab, but it places you better. You take the favoritism that that lab has with you in your next job and so on and so forth. So that's another thing that hasn't really been looked at in terms of experience, and it comes with a whole set of issues itself because of relational dependencies. And the last thing is performance measures. I wanted to put this up. How many of you know about the pneumonia study that was done in the 1990s? A few of you. So back in the 1990s at University of Pittsburgh, they decided to learn whether complications will arise from pneumonia. And they actually learned the perceptron, which is a small version of a neural network. And what the perceptron was very accurate in terms of when, like, Tina goes to the hospital with a pneumonia, whether she would have complications later on or not. But one of the curious things that they found was that patients who had asthma, the algorithm would say they were not going to develop complications from pneumonia. And that's a red flag, right? And it seems like if I have asthma and I go to the hospital with symptoms of pneumonia, by policy, I automatically get a room at the hospital, right? And the neural network, the perceptron, was not seeing that. And the only reason that the Pittsburgh researchers were able to find this was because there was also rule-based approaches that were trying to do this. Right? So this idea of, oh, I'm just going to go for accuracy or robust predictions, especially in healthcare and medicine, is one of those things which is extremely important and so has to be looked at. So there's lots of these different measures of fairness, as you all know. But one of the things is that it seems like the current approaches that are out there, they're trying to get basically fairness to do all the normative work, all of what you ought to do, right? Again, they don't look at the task, for example. And so they ignore this idea of, oh, well, maybe I should build the normativity into the task as opposed to just say, oh, I'm just going to do classification. Easy, I understand it, it's perfect, right? And so you need to be able to spread that through. And so the two take-home messages that I have is, one is we need to incorporate normativity, what you ought to do throughout the entire machine learning process, right? And if you think about machine learning in terms of this triple, you have to build it into the task, the experience, and the performance. And a promising task to look at least from a machine learning perspective, would be apprenticeship learning. And again, it's a hard task. It is not an easy task. It's a DARPA level task. I was just at a DARPA workshop where they're interested in computational ethics, where, for example, for disaster relief or humanitarian aid, you want a robot to be able to make those decisions all by itself without checking back home, right? And if, in fact, if you want to do that again, it would be nice if the robot is trying to imitate a general that's a human exemplar, right? And on that note, I just want to thank A few people. So Danielle Allen at Harvard got me started on this by asking me to give a public lecture. Jack McDevitt is a criminologist at Northeastern who has helped me a lot looking at the COMPAS data. Brandon Feidelson and Ron Sandler, they're philosophers. And thank you for listening. And my slides are up there, and that's my contact information. Thank you.
Okay, questions? Sorry.